Well, it's time to get started. I will begin. Dear Heavenly Father, we thank you for this day. Again, I thank you for this class. For your students, just ask you just guide our steps today, help us to glorify you what we do, and that we'd resolve any questions that might come up along the way, Lord. In my prayer, Lord Jesus. Amen. All right, so surface integrals. Oh yeah, please turn your quiz in if you wouldn't mind. So, to calculate the surface integral, we need, oh, thank you. There you go. To calculate the surface integral, well, all right. Guess I got everybody so far. Thank you, thank you. So to calculate a surface integral, we need two things, right? We need a surface, right? And what else do we need? Well, actually a vector field. So, thank you, sir. And and so if we have those two things, then our definition, right, is the integral of f dot ds over the surface, which I'll call S, is equal to the integral, and the S is actually equal to what? S is actually equal to, let's say, big X of d. So the integration is over the parameter domain d. You take f, you evaluate it at your parameterization, right? And you take the dot product with the cross product of your partial velocities. And as we discussed that, we could call the vector surface area element, or the infinitesimal vector surface area element. So basically this right here is what I call ds vector, right? And last time I worked out, last class we worked out number one, if we have a sphere, right? You know, the sphere, basically rho equals to r, you know, positively oriented. Let's call it S sub r. That's not like a standard notation or anything. It's just the notation I'm trying to use in here. We worked out that in that situation, we have a parameterization, phi theta. It was r cos theta sine phi, r sine theta sine phi, r cos phi, right? Which is was exactly the formula you get from looking at spherical coordinates and just freezing the spherical radius to be rho equals to r, right? So we can derive you know, there you go. We can derive parameterizations of surfaces that are, you know, natural surfaces with respect to a coordinate system, right? If your surface is just what you get from setting one of the coordinates in our standard coordinate systems equal to a constant, then you can use the coordinate formulas just to write down formulas for the parameterization. That's what happened here. And furthermore, sometimes you can write, you know, let's see here. So like this one, ds vector, right? I told you, well, we worked it out, right? And what do we get? We got like, how'd it go? R squared, I guess it was sine squared phi cosine theta, r squared let's see here, sine squared phi, sine phi, and r squared sine phi cosine phi, right? And I emphasized that that was really just equal to r squared sine phi, right? And then you have this vector, which we could identify as rho hat. And so that's another way to write the surface area element, excuse me, the vector surface area element, ds vector, if you like, for the sphere oriented outward. So this is another thing. If you embrace use of the spherical or cylindrical coordinate frames, they can save you a lot of aggravation if your problem has a spherical or cylindrical symmetry. This you will not find in Stewart. All right? It's just not there. But it is a good way of thinking. And you can understand where this ds is coming from another school of thought, which is just like basically geometric intuition. If you look at the sphere and you look at a little sweep through this little sweep here, and then like a little sweep like that. So you've got, so let's see here. This one you could look at as r sine phi d phi, whereas the one, my bad. I gotta get this. I'm a dummy. So this one would be just r d phi. That's the one that we sweep like off the polar angle, or I prefer to call it the colatitude. And then this displacement down here, so that's like your dl phi, the little displacement in phi direction holding theta fixed. On the other hand, since the radius, the cylindrical radius, is r sine phi, we get r sine phi times d theta for the little change in length in the theta direction holding phi fixed. So it's not a mystery why this formula came from, if we are willing to think geometrically. And it's a little bit dangerous because geometry only works in as much as, the coordinates are actually they have to be perpendicularly arranged, ortholinear, if you will, coordinates. Otherwise, well, you can still do geometry, but it requires more care. But here it works out, as you can see. That is why that formula came there. That's why we have that. Because that's the little area that's subtended from a token change in d theta and d phi.
Would d theta and d phi be included in that r squared sine theta?
Oh yes, thank you. Yes, my bad. But anyway, right here. So, if I was going to put something on a formula card, this would definitely be something that I would put there, personally. Well, I guess that's not true. Well, the thing in blue I probably would put there. The thing right above it, I would hope I could derive, Let's look at another example of this. So example 1, we'll look at a really simple vector field. F equals to x hat. Okay, that's a very simple vector field, and let's consider S R, but not the whole thing. I want to say SR just in where with the condition that x is greater than 0. All right, so if I can draw a picture of that. Here's my x. So I'm just talking about if you can imagine this, the forward I should have made it y greater than 0. I can draw a better picture of that. My bad. But to be clear, the back of this, it's cut off. It's chopped back here at the, the YZ plane. So what's going on here is you're going what? Basically minus pi over 2 less than or equal to theta less than or equal to pi over 2, right? Because the theta is just sweeping back to the positive y-axis or negative y-axis, but not beyond it. Does that make sense? And on the other hand, the phi, well, the phi is full sweep, right? It's starting up here and it's going all the way down to there. So I've got 0 less than or equal to phi less than or equal to pi. All right? So a lot of being good at doing integrals with spheres is having a solid understanding of where the spherical coordinates are starting from and going to and how they work. Right? Because if I want to do an integral over a portion of a sphere, it's important that I know how to limit the coordinates, phi and theta, to get that part I want. Does that make sense? So, all right. So let's calculate the flux. Here we go. So we've got the integral over, I guess I'll call this thing S for lack of imagination. And so we're looking at F. I'll start out with my generic notation and then I'll put in what this is. So we've got the integral from 0 to pi, the integral from minus pi over 2 to pi over 2. It's annoying. And let's see here. Poor planning on my part. So I'm sorry, guys. I'll just use an arrow here. Put this up there, okay? So what we're dealing with is, man, I'm very unhappy with this. Anyway, 1, 0, 0. Dot product with this thing, right? And I would say that the notation I'm using right now is not the best, but I'm trying to be, still poor planning on my part. What do I still owe you? You make those tiny. Yeah, I owe, well, this one, I better go d theta, d phi, right? There's no row or anything. Like everything else is already wrapped up in the normal vector, right? So the formula is just f dot the normal vector times du dv, which in this case is d phi d theta. All right. So anyway, that is the integral from 0 to pi, the integral from minus pi over 2 to pi over 2 of what? That dot product's kind of boring, isn't it? It just gets you a what? An r squared sine phi cosine theta d theta d phi. How should we integrate that? Well, I'm going to pull an r squared out. And the bounds are rectangular, so that's nice. Integral from 0 to pi of cos theta d theta. Really? Oh, man. Permission to change the example. Can I? What? No? Oh, man. All right, fine, I'll leave it. What's the answer? And it's obvious. You can tell me the answer here without calculation. Yeah, 0. See, because this integration is 0. And that one is also 0. Goodness gracious. So it's 0, yeah. Why is the integration here 0? What's going on? If I can, draw the, let's see here. So here's our, our half sphere. So I mean it's flat on the back, right? So where does x point? What? Wait. I don't believe this. Maybe, let me draw this picture. These pictures don't do it. Sometimes you have to take a two-dimensional perspective picture to make sure you're on the level here. So for the problem like this, it's helpful for me to kind of just suppress the z and look at y going this way and x going that way. And then the sphere we're looking at is like this, right? X greater than 0. This is a top-down view, okay? Z's coming out of the board. And, oh, right. I'm a dummy. No, my bad. This is not part of it. This is not part of it. It's just well, that's the question. See, the question is in some sense slightly ambiguous because you can ask the question whether or not I'm including the back of the hemisphere. Yes, Daniel?
I think you changed the bound wrong.
I did change the bounds wrong?
Yeah, you swapped t with theta.
Oh. Where?
One of the steps over there.
Like it was this step? Well, that would explain it. Okay, so I was about to get really confused because this is a picture top down, right? So what does the normal vector field to this look like? Something like this, right? This is the outward pointing normal, right? It's more than that because it's like that out here, but then it's like up here like that, right? Down here it's like that. It's out like a spiky ball out. And if you picture x hat, that definitely should give us a positive flux, right? Because x hat is boring, right? It's just, this is x hat. So are the field lines of x cutting through the sphere, half sphere? I mean, yeah, right? Surely we should have a positive flux. And indeed, thankfully, it was pointed out that I have switched my formulas. Oh, whew, what a relief. I was about to get really, really confused. Thank you. So, no longer 0. Now what? Where did I put my pi r squared? And does that make sense? That was what I was after. So the sine phi integrates to 2. Wait a minute, no? Wait, what's sine phi integrate to? Fine, I'll do it. So you got minus cosine pi, plus the cosine of 0 times the sine of theta evaluated from minus pi over 2 to pi over 2, right? How did you get pi r squared? Oh. That's unfortunate. Did I do those integrals right? I am very suspicious of myself now. What's that? Oh, come on, peoples. What else is wrong here? Yeah, what did I copy down wrong? Yeah, I had sine squared phi here. I had my sine phi here, but I'm supposed to have sine squared, right? Does that matter? Oh yes, it matters quite a bit. You mean a little 2 makes a difference? Yeah, it makes a difference. All right, so at least I lost 40% of the credit on this example up till now. Drats. But now the integral of sine squared is a little bit more interesting, right? Here's a trick. If you think about sine squared, well, if you integrate sine squared plus cosine squared from 0 to 2 pi, what do you get? Sine squared plus cosine squared integrated from 0 to pi, what's that? You say from 0 to pi, it's pi, right? But sine and cosine are symmetric about this interval if you look at the totality of the shape that they make. So this integral has to be pi over 2. And then that is 2. So, hey, good news, Sam. Pi r squared. Because that's pi over 2 and that's 2. So. Now, why did Sam say that the integral's pi r squared? Why is the flux pi r squared? If you can envision this, right? Think about this. If you look at this picture here, well, how many field lines are cutting through the half sphere? The same number as if I replace the half sphere with just the disk that's back here, right? That would be the, I can't draw any of it, but that's the disk on the back of it, all right? You know, so if I was to draw it like this, and here's this is x hat, right? So that's, maybe I should draw it like this, all right? On the back side here, the disk on the YZ plane, what is the area of that disk? It's pi r squared, right? So, and that disk, notice that the x hat field lines are cutting through normally. So it's just the magnitude times the area, which in this case is pi r squared. That's why we got that. Sorry it's taking me so long to get to this. What would happen if I did this integral instead of the half sphere, the whole sphere? What would happen? So you're saying I get 0? I think that's right. So example 2, what if I do, let's do f hat equal to, let's do a different one, let's do z hat. You know, find flux through, and let's make it a little, let's level the game up here a bit. Z squared z hat. Find flux through the sphere, the whole thing. All right. I'm not going to mess around this time. I'm going to do it the easiest, laziest way I can do it, all right? So here I was just trying to be faithful to the definition and use what we did last time, okay? Now I will show you how I would prefer that you calculate just to save yourself trouble. So what we do is we simply plug in what's the formula for z on the sphere. The formula for z on the sphere is r cosine phi. All right, so I put an r cosine phi in here, square that thing, right? And of course I'm integrating from 0 to 2 pi and 0 to pi, full sweep for the spherical angles. And my ds, and then I've got an x hat, all right? My bad, what did I have? Did I have x hat? No, I had z hat. So there's my there's my f evaluated at the parameterization. Then I'm supposed to take the dot product of that with what? Well, with rho hat, all right, times r squared sine phi d theta d phi in my current language. What is z hat dot rho hat? What's rho hat? Something I think it would be healthy for you to think about. Rho hat is cos theta sine phi, sine theta sine phi, cosine phi. So you see z hat dot rho hat is simply what? We've got ourselves a r to the power 4. Notice that z hat dot rho hat is what? It's just cosine phi. So man, we got lots of cosine. It looks like we got a cosine cubed phi sine phi d theta d phi. So what's that work out to? Apparently integral from 0 to 2 pi d theta, right? And then let's see here. We've got r to the 4th. I'll pull that out. Integrating over 0 to pi. Cosine cubed phi sine phi d phi. So what would you guys suggest I do? How would I do that integral? Do a u substitution, right? U equal what? Okay. Then du is minus sine phi d phi, right? And there's a kind of funny thing that happens with this substitution, right? What's u of 0? Oh, it's not that funny. I was hoping it would be funny. It's not funny at all. It's just, it is what it is. U of 0 is 1. U of pi is minus 1. You're like, wow, you're actually changing the bounds? Yeah, fine. I'm actually changing the bounds. You happy? So we got 2 pi r to the 4th integral 1 to minus 1 of minus u cubed du, which of course we can trade for 2 pi r to the 4th. That integrates to u to the 4th over 4, evaluated from minus 1 to 1. So I flip the bounds and absorb the minus. All right? The larger point here is we get 2 pi r to the 4th times 1/4 minus 1/4, also known as 0. Why is this completely unsurprising? Well, maybe it's not. Maybe that's too far. Maybe it's not. It may be surprising to you at the moment, but it should not be surprising to you after you're done with your studying in this part of the course and like have absorbed the material. See, because I can draw this picture of the sphere suppressing the x direction. All right. Well, this is just kind of a schematic of it, and what's going on here? F of z is z squared z hat, right? So what's that look like? It looks something like, I don't know, like this, right? I'm not even trying to really, well, it's 0 here, right? Really close to the equator. It's really close to z equal to 0. It's super tiny, and it gets biggest at the poles, right? But z squared is what? It's symmetric above and below the xy plane, right? It's the same story. So these would be replicated, like they're the same, whatever their height is, they'd be replicated, on the other side. But what do the normals to the sphere look like? They're always outward pointing, right? So the normals to the sphere are arranged in such a way that everything that was a plus is now a minus, and exactly the opposite way if you look at the northern versus the southern hemispheres. So I expected the answer would be 0 here before I wrote down an integral. I would also expect that if I was to limit the angle, right? So can you tell me what would make the flux positive for this example? What if I did? If I just had, say, the upper hemisphere, I should get a positive flux, right? So how would this problem change if I was just doing the upper hemisphere? I would just, instead of letting phi go from 0 to pi, I would let it go from 0 to pi over 2, right? And that pi over 2, instead of pi, would have changed that to 0, all right? Which would have ended up giving me, you know, pi r to the 4th over 2 for the flux. On the other hand, if I just do the lower hemisphere, I would go like pi over 2 to pi, and I would get minus, you know, pi r to the 4th over 2. So you can see that from the calculation here. But you should try to develop some intuition about whether the answer should be positive or negative if the vector field is sufficiently like uncomplicated, right? Now there are going to be some examples that we do that I'm just not going to be able to tell you intuitively like what's going to happen before we do it, all right? Like it's just the nature of the beast. So for example 3, let me just do another one here. So this one I'll do something rather different. We'll let z equals to x squared plus y squared, where 0 is less than or equal to x squared plus y squared, less than or equal to 1. All right? And so oriented downward. In the z sense. Okay. All right. Let me try to explain what I mean by that. What does this thing look like? What is z equals x squared plus y squared? Do you guys remember? Nobody? Yeah, a paraboloid, right? And so a picture of this thing is something like this, right? What I'm trying to say is I want the normals to be pointing downward for the sake of this example. All right? And I'll tell you guys, like, I don't know right offhand how I should do that. I just don't remember right offhand, all right? Now in the notes, I have, as one of the cases, how to set up the flux for a graph, right? So like if you have a vector field, you're calculating the flux through a graph. That's one of the numbered examples here. But we can work it out. So in this case, what's my parameterization? We could use x and y, right? It's kind of boring, but there it is. So here's a parameterization of this thing. We'll use x for the basically think of u equals to x, v equals to y. I'm just going to try it that way, and if it works out like I want, great. If it doesn't, I know how to change the orientation. I just flip which one comes first, x or y, and that'll disorient it. So let's see what happens here. So the parameterization, I'm saying x, y, and what's z? Well, z is x squared plus y squared, all right? So there's my parameterization. My partial velocity in the x direction, partial big X, partial x is 1, 0, 2x. My partial velocity in the y direction, partial y, x partial y, is 0, 1, 2y. My normal vector at xy is the cross product of those two things, which is what? So let's see here, x hat we get minus 2x. The y hat we get minus 2y. And the z hat we get 1. Aw, man, as you can see, that points which direction?
Positive z.
Positive z, right? This points up. Up. Which is not what I wanted. I want it to be oriented downward because that's what I said. Now, do we always want it to be oriented downward? No. It depends on the question. Anytime you're given a surface integral, you must demand, it is your right as a student to know whether that surface is oriented, in which way it's oriented. Because there are two choices. There's two choices with any surface. You can integrate it, you could set the normal on one side or the other side, right? It's your choice. So what I should do then is just use n, this is very stupid, but I just do y first and x second. If I just switch the order of the parameters, then that makes this, partial x, partial y, cross partial x, and then that, by the same, everything we just did, is going to be 2x, 2y, minus 1. All right? Hooray. So, all of this setup has nothing to do with the vector field which we're finding the flux of. Yep.
Aren't we always supposed to pick the field that's radially outward, though?
No. No.
For a closed surface?
For a closed surface, Sam's right. By default, the positive orientation of a closed surface is the outward oriented normal. But you could do an integral of a closed surface with respect to an inward oriented normal. We're gonna write down theorems eventually. So you know how the theorems we've had up to this point have been natural for counterclockwise curves? Well, on the outside, and then they have to be clockwise oriented on the inside. There's a similar story for theorems about surfaces where we have to have the outside edge outward oriented, and if there's an inside edge, it has to be inward oriented. So that kind of plays the same role as like clockwise and counterclockwise for the other thing. But anyway, we'll get there. Let's focus on this one. So you guys can give me any vector field you want. We can try to calculate the flux through this partial paraboloid. So, what do you guys want for the vector field? F of x, y, z equal to what? Don't make it too hard because I want to do the integrals. Like no inverse hyperbolic tangents, right? In fact, I'd prefer polynomials. All right, nobody? All right, fine. How about x, x squared, and yz? There, I'll regret this. There you go. That's a vector field. I certainly don't want to try to picture this one. I have zero intuition about what's going to happen for this, all right? I'm just going to calculate, see what happens, see what the flux is of this vector field through that paraboloid. How do I do that? Well, here you go. The integral, I guess I should give it a name. I'm going to call this one Bob. So the flux of the vector field through Bob is so I'm supposed to integrate, do the double integral over 0 less than or equal to x squared plus y squared less than or equal to 1 over that. What's that? Well, that's the unit disk, right? And then all right, so I'm supposed to take f and I'm supposed to evaluate f at my parameterization. So that looks like, this one's pretty easy to evaluate, right? X is X, and Y is Y. What's Z? Z here is equal to X squared plus Y squared. So if we're using X and Y as parameters, everything except for X and Y has to go away in the process of the integration. And then we're taking dot product with, well, 2x, 2y minus 1. And then that's integrated over dx dy, right? So you take the dot product. That's not too bad. It occurs to me that I can just as well say x squared plus y squared less than or equal to 1. The fact that it's non-negative is automatic because of the expression. So what do I got? I've got a 2x cubed, right? Plus 2x squared y. Was it? Oh, yes, thank you. Many thanks. And then minus y times x squared plus y squared, right? Dx dy. All right. In fact, if I, oh no, I can't do that. Okay, that is what it is. All right. So what's the integration region here? Right? If I draw it like that, despite my picture, it's totally symmetric with respect to x and y, right? Goes from +1 to -1 and so forth. Are any of these expressions automatically 0 when you integrate them over a whole disk? Are any of those expressions like odd in the sense of just one variable? Well, I know, just if we think about this expression right here, right? X squared plus y squared is the same with regard to any of these 4 quadrants, right? If I integrate x squared plus y squared over any of the 4 quadrants individually, that would be the same. But y is positive up here, it's negative down here, and symmetrically so. So I can tell you, before I do any more work, that this integrates to 0. This piece. 0 by symmetry. Likewise, this integrates to 0 by symmetry. Because x squared is symmetric, you know, and the x squared is symmetric for positive and negative x, but on the flip side, the y, positive up here, negative down here, and equally so. So that piece will also integrate to 0. Looks like I've only got to integrate 2x squared. How should I do that, though? Should I accept my fate and work this out in Cartesians? Certainly not. So what we'll do is integrate from 0 to 2 pi, integrate from 0 to 1, and then we've got 2 r cosine theta, quantity squared, times r dr d theta. I'll use polar coordinates to do this integral because that's what I should do. Yeah? And so you do that, and you got yourself an integral from 0 to 2 pi of cosine squared theta, d theta. I can pull out the 2, and then I've got an integral from 0 to 1 of r cubed dr. Think about this. If I have cosine squared plus sine squared integrated from 0 to 2 pi, I get 2 pi. But cosine squared is half of that story, and symmetrically so. So the integral from 0 to 2 pi of cosine squared is just pi. And then, of course, I've got 1/4. So the answer is pi over 2. Don't even ask me to picture this. I don't even want to try, but we can calculate the flux without much effort. Now, that is not always the case, right? I mean, the calculation of flux is, it's a double integral, right? It's a double integral that comes after what? After the cross product, right? So, what's next here? I probably should show you guys the notes. I never am successful in like writing out all of these on the board, and that's kind of not the point here either. I'd rather work 3 examples slowly than hurry through writing up 5 things that are in the notes. But I do want to make sure that we're on the same page about what's in the notes and how you can use it. So let's do that. If I can get it. Whoa. Did you already move it up? No. A question? Yeah. Oh, yeah. If you haven't given me your quiz yet, that would be good. Oh, maybe we could top hat. I keep, you know, I have deprived you guys of top hatting. We should do it like 4 times. Well, I don't know. I'm not sure. I still have things I actually. Well, maybe we can do it 5 times tomorrow. How about that? Oh, I did want to hand out the attendance sheet. You can add a date to there. It's been a minute since I turned that one around. As you guys know, I do care about you coming to class, and I don't, you know, take points off directly for that, but it's just a fact of the way things work that, you know, when you don't come to class systematically, it will hurt your grade. I don't really need to take points off. You know, you take those points off by yourself. You know. Let's see here. So, come on. I rebooted my computer, and in so doing, closed all my notes. All right. So, we could also talk about how to parameterize a cylinder, right? Come on, laser. I've lost my laser. Wait, is that? No, that one's. Here we go. Oh, really? I tell you what, it's so annoying. So for a cylinder, notice what I do? I just put little r equal to big R, that's a cylinder. Freeze it out. That gives you the parameterization. You calculate the cross product. Lo and behold, we get the ds vector is r d theta dz r hat. You could again look at that as a little change in the theta length, a little change in the z length. That gives you ds. So that's how we would do an integral over a cylinder. A cone. How do you get a cone? Well, if the cone is a pretty standard cone, based on the z-axis, to get a cone, you just freeze phi equal to a constant, and that gives me the parameterization. I calculate the normal by taking the cross product, and it turns out the normal points in the phi hat direction. And so here's a formula for ds. We'll do examples with these in future days, okay? And then we did the plane before. Graph, we actually did one of these today. This is mostly what Stewart does. Is if you've got a function, you can parameterize it by Cartesian coordinates if it's the graph. And the upward pointing normal is this, right? And so ds vector looks like this. If you want to calculate the surface area of a graph, it's the magnitude of this, which is that. And so if you want to calculate the area of a graph, you do that. If you want to calculate the area of any of these examples, it's just integrate the magnitude of the ds, basically. And then I have examples, but so the other thing I should mention while I have this out, because we're dragging a little bit behind here, is that right here, what I do is I suppose I have 2 different parameterizations for a surface, and I calculate like partial r, partial u, and compare it to the x derivatives with respect to the parameters of the other parameterization. I call them a and b. And so like if I had two different parameterizations involved, then I get this chain rule relating the partial velocities of the two. And what that allows me to do then is to try the surface integral in two different parameterizations. And when I compare the normal vector field with respect to the one parameterization to the normal vector field with respect to the other parameterization, they end up being related by this quantity right here. But what is that? Well, that's nothing more than the Jacobian determinant of the transformation that switches one parameter to the other, which then, by the change of variables theorem, gives you that the flux calculated with respect to the r parameterization is equal to the flux calculated with respect to the x parameterization. Lo and behold, our definition of flux is independent of our choice of parameterization. I have never presented this in class properly, so you guys have that in common with all my other calculus 3s. Hooray!